Why Stenon mechanics may be closer to physical reality. A logical assessment. Introduction. Throughout the history of science, progress has often occurred not by discarding successful theories, but by asking deeper questions about the physical reality behind them. Newton explained planetary motion through gravitation. Einstein explained gravity through the geometry of space-time. The next natural question is, what is the physical nature of space-time itself? Stenon mechanics is proposed as an attempt to answer this question. Its significance lies not merely in introducing new equations, but in attempting to provide a mechanical and ontological explanation for phenomena that general relativity describes geometrically. This article examines why, from the standpoint of logical structure and explanatory completeness, Stenon mechanics may represent a framework closer to physical reality. Science seeks mechanisms. Physics has traditionally progressed by replacing abstract descriptions with physical mechanisms. Heat was eventually understood as molecular motion. Light became understood as electromagnetic waves and later as quantized photons. Electricity was connected to electric charge. Again and again, successful mathematics was eventually accompanied by a deeper physical interpretation. Stenon mechanics follows this historical pattern. Rather than stopping at the mathematical description of gravity, it asks, what physical medium gives rise to the observed gravitational behavior? A physical space, rather than an abstract one. General relativity successfully describes gravity through space-time geometry. However, it treats space-time itself as fundamental. It does not specify a physical constitution for space-time. Stenon mechanics proposes that space is itself a real physical medium. Within the framework, this medium is proposed to possess measurable mechanical properties, including density, compression, tension, equilibrium, and universal coupling with matter. If such a medium exists, then gravity can be interpreted not merely as geometry, but as the large-scale behavior of a physical system. Mechanical quantities, instead of pure geometry. One distinctive feature of Stenon mechanics is that it introduces explicit mechanical quantities. The framework proposes, among other parameters, a universal tension of space. These are proposed physical quantities rather than purely geometric descriptions. Whether these quantities correspond to nature remains to be determined, but they provide a concrete mechanical framework that can be analyzed, refined, and tested. Gravity as compression equilibrium. Within Stenon mechanics, gravity is interpreted as the result of compression gradients within the proposed space medium. Matter modifies the surrounding mechanical state of space. Objects respond to these gradients. This replaces the question, why does curved geometry influence motion? With, how does the mechanical state of the surrounding medium influence motion? This shifts gravity from a purely geometric description toward a proposed physical mechanism. Neutron stars as mechanical evidence. One of the central ideas of Stenon mechanics is the interpretation of neutron stars. These objects represent some of the most extreme stable structures known in nature. Within the framework, neutron stars are interpreted as systems in mechanical equilibrium. The proposed compressive action of the surrounding space medium is balanced by the extraordinary internal resistance of neutron star matter. This interpretation provides an intuitive mechanical picture. Space compresses. Matter resists. Stability emerges from equilibrium. Whether this interpretation is ultimately confirmed is a question for further theoretical and observational work, but it offers a unified mechanical explanation within the framework's premises. Black holes as dynamic restoration of equilibrium. General relativity describes black holes geometrically. Stenon mechanics proposes an additional mechanical interpretation. As a massive star collapses, the surrounding medium is hypothesized to move toward restoring mechanical equilibrium around the collapsing region. In this picture, the inward behavior associated with black holes reflects the dynamics of the proposed space medium, rather than geometry alone. This interpretation seeks to provide an ontological mechanism underlying the geometric description. Explanatory economy. A powerful scientific theory should ideally explain many phenomena using a small number of fundamental principles. Stenon mechanics attempts to do this through concepts such as compression, tension, density, equilibrium, and universal coupling. Within the framework, these principles are proposed to account for gravity, gravitational lensing, neutron star stability, gravitational collapse, black holes, and potentially other gravitational phenomena. Whether this unification succeeds depends on mathematical development and comparison with observation, but the logical aim is one of conceptual economy, a complement rather than a rejection. Stenon mechanics does not need to reject Einstein's achievements to be significant. General relativity may be viewed as an extraordinarily successful geometric description of gravity. Stenon mechanics proposes that this geometry could emerge from the behavior of an underlying mechanical medium. If so, then Einstein's theory would remain valid as an effective large-scale description, while Stenon mechanics would provide a proposed ontological interpretation beneath it. In this sense, the two frameworks need not be viewed as enemies. One describes geometry. The other seeks to explain why that geometry exists. Conclusion: every new scientific framework begins as a hypothesis. The value of Stenon mechanics lies not in declaring victory over existing theories, but in attempting to answer questions that remain open regarding the physical nature of space. Its proposed concepts of space density, universal tension, compression equilibrium, and mechanical coupling form a coherent conceptual framework that aspires to explain gravitational phenomena in mechanical terms. Whether these proposals ultimately describe reality will depend on rigorous mathematics and successful empirical testing. If they do, Stenon mechanics would represent not merely another theory of gravity, but a proposed bridge between geometry and physical mechanism, continuing the long scientific tradition of seeking deeper and simpler explanations for the workings of the universe.